At 8:15 a.m. on August 6, 1945, a blinding, semi-spherical flash of light consumed the sky over Hiroshima. This photograph captures the exact fraction of a second a nuclear detonation unleashes its energy, and this is the immediate aftermath. Within seconds, a bustling city was reduced to a flattened landscape, leaving roughly 70,000 people dead almost instantly. But the initial blast was only the beginning. Another 70,000 to 80,000 people who survived the explosion soon perished from radiation fallout, their cells breaking down from invisible poisonous energy. The explosion also triggered a secondary horror, a firestorm. Look at this diagram. As the immense heat of the bomb violently rises, it leaves a void near the ground. To fill that empty space, freezing air rushes inward at hurricane speeds. Notice the debris markers being pulled into the vortex. The rushing air acts like a massive vacuum. The wind speeds became so intense that survivors trying to flee were physically dragged backward, straight into the burning center. In 1945, the world possessed exactly 2 of these weapons. Today, there are over 12,500 active warheads distributed across the globe. Each one is roughly 80 times more powerful than the bomb dropped on Hiroshima. A modern exchange wouldn't end with localized destruction. The smoke and debris from thousands of simultaneous detonations would trigger a prolonged global freeze. The true threat to human civilization is the nuclear winter that follows. The physics making these weapons possible was calculated in absolute secrecy. This is the main gate of the Los Alamos project, the remote facility where scientists gathered to build the first bomb. During those early preparations, physicist Edward Teller, seen here, ran a terrifying calculation. Earth's atmosphere is 78% nitrogen. Teller's math suggested the extreme heat of a nuclear blast might trigger a runaway chain reaction, literally setting the entire atmosphere on fire. To check this apocalyptic theory, the team turned to Hans Bethe, pictured here on his Los Alamos ID card. As the project's chief calculator, Bethe's job was to determine the exact probability that their upcoming test would incinerate the planet. Bethe ran the numbers repeatedly and concluded the chance of atmospheric ignition was almost zero. For J. Robert Oppenheimer, leading the project, almost zero had to be enough. He ordered the team to keep the theory strictly confidential, knowing that public panic or a loss of government funding would kill the project. They rolled the dice and the atmosphere survived the test. But while these physicists were focused on the heat of the blast burning the sky, they completely missed the opposite outcome, that the smoke from their creation could permanently block out the sun. It wasn't until 1983 that a team of 5 scientists formalized this threat. In this photo, Dr. Carl Sagan presents the findings of the TTAPS research paper, going on television to warn the public about a devastating karmic collapse. The mechanism works like this. If a large-scale nuclear exchange occurs, cities and forests burn, sending roughly 1 billion tons of black smoke high into the air. This soot rises 15 kilometers into the stratosphere, placing it well above the rain clouds that would normally wash it away. It spreads, forming a global shield. Watch as the soot layer thickens here, deflecting the sun's rays back into space. Global temperatures drop to an average of -25 degrees Celsius. Without sunlight penetrating the atmosphere, the process of photosynthesis abruptly stops. This creates an immediate biological collapse. Crops in the field die within days, turning to dust at a touch. The rain that does fall from the lower atmosphere is heavily radioactive, poisoning local groundwater supplies. At the same time, the electromagnetic pulses, or EMPs, generated by the blasts, fry the world's electrical grids. Transportation, communication, and supply chains instantly freeze. The blast radius is relatively small compared to the global impact. For the billions of people who survive the explosions, they are left in a dark, freezing world, where starvation claims their lives over a 3-year winter. This outcome doesn't even require the US and Russia. A localized nuclear exchange between regional powers, like the border tensions between India and Pakistan shown here, would generate enough atmospheric soot to plunge the entire planet into winter. Surviving this scenario requires extreme adaptation. With the sun blocked, traditional agriculture is useless. The solution lies in large-scale subterranean vertical farming, like the facility pictured here, relying entirely on artificial LED lighting to sustain crops. To maximize yield in limited space, humans would need to pivot their diets. These raceway vats are cultivating spirulina. It's an incredibly dense, high-protein algae that grows rapidly with minimal light, a survival model already tested during economic crises in places like Cuba. Growing food requires power, which brings us to the EMP threat. Notice this heavy metal mesh surrounding the equipment. That is a Faraday cage. Shielding critical medical and energy infrastructure inside these enclosures is the only way to protect them from the massive electrical surges of a blast. On the medical front, radiation poisoning will spread far beyond the impact zones. Governments need massive distributed stockpiles of potassium iodide tablets, shown here, to protect civilian thyroids from absorbing radioactive isotopes. But infrastructure means nothing if the public panics. Historical movements like these civilians protesting radiation dangers show that people demand transparency. Educating the population now on emergency protocols and early warning systems is critical to maintaining order. Underground farms, Faraday cages, and iodine pills can keep a fraction of the population alive. But in a nuclear war, there are no victors. The only way to survive a nuclear winter is to ensure the first bomb never falls.